All right, so while Ravi's getting set up, all right, our next speaker of the night is Ravi Yelleswarapu. Ravi is a third-year bioengineering PhD with the goal of inventing microchip-based tools that enable accessibility to medical diagnostics in resource-poor settings. He went to undergrad in Boston University, where he majored in biomedical and electrical engineering to work at the interface of these two fields. He's also been interested in commercializing technology and is involved in programs such as PBG, PCI Fellows, and a startup spun off from their lab. And a fun fact about Ravi is that back in high school, Ravi was the #1 player in the world in one aspect of the online video game RuneScape. You can ask him about that later. And he had quite a YouTube following with videos that he made.
Yeah, very proud of
that. And we'll leave it to Ravi.
All right, so hey everyone, I'm a third-year bioengineering PhD in David Zitter's lab, and the work that I do is trying to detect single molecules of DNA, RNA, and protein to detect very rare diseases that you typically can't using other techniques. The main thing we want to do is we want to build a commercial platform that's also mobile that you can take out into the field. The way we do this is we combine two separate fields. The first is microfluidics, which takes stuff that you do in a big, large lab setting, and you can put it onto a tiny chip that's about the size of something that you can hold. And I have some friends that are going to pass around some of the chips so you can look at them for those of you who have never looked at a microfluidic chip. And the second step is we want to combine this with microelectronics. So there's been a lot of advances, especially in things like computing power, where within a cell phone you can now have the computing power to look at the videos and everything that you want to look at for diagnostics, and then also connect that to cloud computing as well as optical detection with this sensor, the camera sensor built in. But before I get into how we do all of this in a mobile platform, I want to talk about why this is important. And there's a huge clinical need for detecting these rare diseases. And the main problem is, let's say you get a blood test and you want to find out if you have cancer or not. The best way to treat cancer is if you get it early. But the biggest problem is if you look in that 1 ml of blood that you get from a blood test, you might have 100 targets that you're looking for. So these are the cells that will tell you whether you have cancer or if you don't have cancer. But within those 100 targets that you're looking for, you also have billions of red blood cells in there and millions of other white blood cells. So basically it becomes a needle in the haystack problem where you have a ton of hay and you have very little needles that you care about, but the needles also look like the rest of the hay. So it's really hard to tell, like, what are you looking for, and the stuff that you care about that will actually give you the information. And the second reason it's very important to get this ultra-sensitive diagnostic is that if you look at cases such as with patients with HIV, once you start treating them with the drug, what happens is the number of antigens starts going down and you really don't know if that drug is working anymore, and you might relapse into getting the disease again. And the idea is if you can monitor how many proteins and DNA and RNA is involved in that blood, you can basically get a really good sense of what's happening inside the body and give the proper treatment. But this is where the problem is. So if you're trying to detect 100 of these rare copies in the background of millions and billions of other genes, it basically becomes impossible because what happens is you can't really tell the traditional technique. So it's the one on the top. You can't really tell whether you have 0 in there, 100, or 1,000 copies, mainly because all that other junk in there messes up your signal, and you get a lot of false positives. So if you're trying to get a cancer test, you can't really tell if you have cancer or not. But luckily, in the last decade, there's been this huge advance with these digital assays. And the idea of digital assay is you take a volume that you have that's really large and contains everything you care about, and instead of looking at that volume at once, what you end up doing is that you break it down into millions of compartments, and what that does is you now have very tiny droplets that are on the scale of 40 microns in diameter. And what that means is if you look at inside this tube now, you basically have your target DNA or protein you're looking for, and the background is basically gone. Because you have millions of these tiny compartments, you're comparing one of the target DNA in the background of nothing, or maybe one other random gene. And with this, you get a very powerful sensitivity and specificity to what you're looking for. And once you just count up the fluorescent droplets, it's very easy to tell the exact number of copies that you have, and then you can make diagnostics. And in the past decade, people have used this as a research tool for a variety of different diseases, from cancer to traumatic brain injury, HIV, and you can name like a ton of different assays that have been built with this. But the biggest problem is it's still a research tool. If you look at it, the main problem that you haven't seen these in the clinic or in the field is the commercial settings that are available for these. You end up having these machines that are really large, so you have 4 separate machines. We have to make the droplets and transfer them, and you have to have a trained technician do all of this. And the second problem is you might have something that's the size of a fridge. So you're talking about something that costs over $100,000 with very expensive machinery in it that you can never take into a field. So what we envisioned is we have this perfect assay that is very robust to noise that you can use in a point of care setting, but you can't do that because it's very expensive right now, and you have you basically have these big machines. So the idea of why it's very complicated is, first, you have to take that sample that you get from a patient, and you have to make 10 million droplets from it. So that's a process in itself. You have to make all these droplets one at a time. And the second is you have to collect all these droplets in a reservoir, so these are droplets going through. And the third is, once you perform the biology assay, you can see that some of them light up over time. So as they light up, it indicates that they have a gene or protein that you're looking for inside there. So once you have 10 million of these droplets, you have to count which of these are fluorescent, and then you get the exact reading of the genes you're looking for. So you can imagine this is very complicated, and the reason that the systems are there right now is they basically took something that was already built in cell cytometry and just used that for droplet microfluidics without really innovating the engineering. So when I came into my PhD, I started talking with my PI visitor. We talked about what can we do in the engineering aspect to really shrink this down into something that we can use in the field. So when I came in, the goals that we talked about were, let's make this 100 times faster, but at the same time, we're going to make this 100 times cheaper and make it from the size of a fridge to something that you can hold, and also all self-contained. So get rid of all the people moving it between the different parts and get a sample to answer. And at this point, I thought it was crazy because how am I going to take a $100,000 device and make it something that you can use on a platform that is on the size of a cell phone, and then get all these very sensitive measurements? So it seemed crazy, but the rest of my talk is to show you that we can do it, and to show you that each of these different parts we have been working on for the past 2.5 years, and how I'm going to address each of them. So first is, let's say you get that tube of blood from the patient, you have 100 cells you care about, and the millions of cells that you don't care about. So what we showed in a paper a while back is that by magnetically isolating the cells that you care about, you can make these filters. Again, this is the size of a chip. So I think I passed that around, but you put the blood in the reservoir, which is very tiny, right up there, and then when you draw it out, when you put a magnet underneath it, all the magnetic cells get trapped on the filter, and all the cells you don't care about come through, which means that when we ran this in the flow cytometer, what we saw was all the leukocytes that we don't want messing up the background signal and giving us false positives. We can eliminate them, and we can eliminate them really quickly, so we can run this at 180 mils per hour. And those of you who have worked with microfluidics knows that this is really fast, and we can go 100 times faster than what people typically use. And what that means is that now we have the cells we care about, and the cells that we don't care about are basically gone. But the next step is you have these cells, and you want to actually look at the genes and proteins inside them, and use that to determine if you have cancer or a certain disease or not. And to do that, you have to put them inside droplets, and the problem we saw here was that if you're making 10 million droplets, it's going to take you anywhere between 3 hours to 14 hours using typical systems, and we wanted to make this go a lot faster. And by a lot faster, we wanted to go 1,000 times faster. And the way we did that was, instead of having one droplet maker, we asked, could we put 1,000 of these on a single chip? And the one I passed around has about 8 of them. So the way we put 1,000 of them on a single chip was we controlled the resistances of the different channels. And the main challenge we solved here is that if you go from one droplet maker, which requires 2 syringe pumps, to 1,000, you would have to have 2,000 different pumps pumping everything. And that obviously is not going to work. So what we ended up doing was we were very clever with this ladder geometry, which you don't need to worry about. But what that means is you can still only have 2 inputs and have 1,000 of these droplet makers and go at liters per hour as opposed to milliliters per hour, which is what people typically do in the field. So we basically killed that goal, and we can go much faster than we ever need to for a biological assay. But up until now, what I've been showing you was water and oil droplets, and what we really care about is putting DNA and all the other stuff in there, and that's what I'm currently working on right now. And the problem with just putting DNA and all these other salts in there is that it messes up the stability, and I've been working on that for the past couple months, and we got some really good results so far. And the idea is, once you put these proteins inside, you want to amplify and see if you have the target or if you don't have it. The way we do that is pretty clever, I think, in terms of the setup is very similar for both DNA and RNA. And in the simplest sense, what that means is you put the target you care about in one inlet, and the stuff that lights up in the other inlet. So for DNA, you put the template and the probes that you're looking for that DNA in the 2 separate inlets, and when both of them come together, you have a fluorescent droplet. For proteins, it's pretty much the same setup. You have a bead that has a protein complex, and then the stuff that lights up, and then when both of them are together, you get a fluorescent droplet. And the really cool part about this is that we wanted to go really fast, but keep this on a very compact chip. And the way we did that was we combined 3D microfluidics where we stack chips one on top of each other to get this high throughput manner and still detect everything. And I think this video demonstrates that we can do digital assays. So the one on the left shows that we have a lot of protein, which means that every single bead, I think you can see the green dots inside the droplets, right? Right, yeah. So the idea is every single bead has a protein on it, which is why all of them are lighting up. But on the right side, what we do is we have less protein than we have beads, which means that basically only that single droplet is going to light up over time, and all the other droplets that have beads that haven't captured enzyme will not light up. So we basically demonstrated that we can get very high throughput system that can look at single molecule sensitivity with proteins and put this in a reservoir. And the really cool part is this stuff gets really bright, so when you put this in front of a cell phone, you can actually see it. So that's a raw image from a cell phone that I took. You can see that there's one bright droplet in the background of everything else that's empty. And once you process all this, it becomes a lot better. But this is a static image, which means we just took a snapshot. And what we really care about is that high throughput system, right? And that's where we come with the next part of the project, which is trying to detect these droplets as they go through really quickly. And the thing we cared about was instead of having a 14-hour time to read out 10 million droplets, we wanted to do this really quickly and on a cell phone. And that's where we came up with the cell phone microfluidics, which we just published last month, and it actually works pretty decently. And the idea behind this is that if you have a conventional digital assay, what happens is you make the droplets one at a time, and you detect everything one at a time with a very powerful photodetector, which means every time a droplet that's fluorescent goes by, you get a very sharp peak. But with the cell phone, we have the same theme of parallelizing everything, so we keep putting more of these channels at once. And the main thing is, since you have a really large field of view with the cell phone, you can look at 120 channels at once, which gives us the high throughput that we care about. And with that, we solved the high throughput issue, but we came with two other problems. The first is we don't get the dynamic range. So if you have a droplet that is very bright when it goes through, because the cell phone only has 60 frames per second, that basically means you get a streak instead of looking at a very sharp point, which you see here. And the way we solved that was that if you have two separate droplets going through you, it's really hard to tell whether you have 1 or 10 different droplets in there. So we borrowed a technique from radar in electrical engineering where instead of having just light on all the time, you basically stroke the LED so it makes a special pattern called the maximum length sequence. And the idea behind that is that if you have different droplets that are overlapping, this dynamic range issue is basically solved because now with this MLS pattern, once you look for that special MLS, you get two very sharp peaks even if things are overlapping, and we showed that we can get very high dynamic range. And the setup, again, is very simple. So here's a setup of what we do in lab. Basically I have this phone and then the microfluidics underneath it and the LED that lights up and gives the fluorescent signal for it. And I also wrote an app. So typically most people that run this stuff basically have a desktop where they end up running all the code, but I just wanted to have a cloud computing app where you can transfer everything, and we got that done. And finally, you can see that these are the 120 channels where the droplets are going through. So we get that ultra high throughput detection all on a cell phone. And the idea is now that we have a cloud computing app, we can basically get rid of all that cumbersome technology that people need. And finally, here's to show that we can actually detect very low concentrations of dye inside these droplets. And that once you start packing them, where they start merging, and you think it's impossible to resolve them using this correlation technique, you can in fact cover 6 orders of magnitude, which is insane for, or which is pretty good. But, yeah, I'm pretty excited about it. But yeah, so do people really care about this? So we have this platform which we think is mobile and has this ultra-sensitive measurements, but what does the commercial world think? And luckily, the two main competitors, Bio-Rad and Raindance, just merged. One bought out the other for a $100 million acquisition, and this was all over the news. If you looked at NASDAQ, Wall Street Journal, people really care about this stuff. And the third competitor, Samoa, they really care about having a mobile platform that they can take into the field and use it for stuff like NFL, where they can monitor traumatic brain injury. So we think that this is really cool, and luckily we started a startup last year, and we just got the second round of funding for it last month from IP Group, and we call it Chip Diagnostics, that basically takes this and tries to measure these rare molecules inside different applications, which I guess I can't talk about right now. And the idea is, hopefully I've convinced you that we can take that fridge-sized device and we can in fact put it onto a cell phone by using the innovation from engineering, from microfluidics, and microelectronics. And the part that I really care about for my PhD is that at the end, really want to, we're starting collaborations with the medical school, where we're getting samples for looking at HIV patients or cancer patients and trying to detect these rare molecules. And for me, if I can get people that have no background in engineering or any of this works, and say after they run it, that was easy, and that they can actually detect all this stuff, that will make me super happy. And with that, I'd like to thank my lab, and the funding sources, IP Group, and Microsoft for funding my PhD, and I'll take any questions.
All right, any questions? Scott first.
How many discrete manufacturing, suppose you work everything out.
Yeah.
How many discrete manufacturing events go into the assembly of the final product?
Yeah, so I don't know if you saw the chip that has everything in it, but there's two parts right now that we're making out of PDMS and glass, and then there's one part that's out of mylar that we're 3D stacking. We're actually talking to a company that says that they can roll out all the PDMS. So instead of having a mylar stuff in between, they can actually roll out everything at once, and they're claiming that they can do it in a monolithic process. And right now, the other options are either go from there to like plastic injection molding, but we're actually going to see if we can get that rolling out method. Yeah, so basically, the first two pieces of that takes one step, and the middle part takes another step, so it's 3 main manufacturing nodes. Yeah.
So how many cancer cells do I have to have before I get cancer?
So you can't just look at only the cells that, just by quantifying them, you really can't tell. So what we end up doing is we have to break that cancer cell down and look at the genes inside it, because it's very hard to tell just by the numbers. So you have to look at, you have genes that are associated with cancer and the proteins in there. So it's hard to tell by number, but if we can collect 100 of them, that's good enough to give you a good diagnostic.
And you know they're all the same sort in that 100 batch?
No, so that's the reason we have to break them open and look inside. So there's different ways to like separate them, and what we do is negative selection, which means we basically get rid of all the junk and only keep the stuff that, so everything that we know is not cancer gets trapped, and the stuff that gets through, it might be cancer, it might not be cancer, but that's why we open those cells up and look inside and see what's in there.
And nothing bad gets thrown away?
So we actually did a measurement where we put in 3 cancer cells, and we put a lot of other stuff in there, and all the cancer cells did go through. And the reason is, in biology, a lot of the parts in the body inherently have no magnetic response. And because we use immunomagnetic sorting, all the stuff is not impacted by magnetic fields unless we tag them manually.
Thank you. Very interesting.
So this might be maybe naive about like the properties of the particle.
Yeah.
Do you anticipate any situation where you have something like in this human sample that would interfere with, like, would compromise the integrity of the particle, or is that gotten rid of before?
Yeah, so there's a few things. So if you're talking about the droplet stability, if you have stuff in there that messes with the stability of the droplets, that was a huge problem that I had to solve when we just put in salts in there. So that's one thing we care about. The other thing is you might get false positives, or the PCR reaction might not actually take place. So things like if you're looking at the stuff in urine, like urea is an inhibitor of PCR, so it might not work if you have urea in there. But the good thing is, once you put it into droplets, the concentration of those stuff go down a lot, so it's not as much of an impact. Or people have shown that. I haven't tested it yet.
Great, any more questions? All right, let's thank Ravi. All right, and can we just get one more hand for all of the speakers? Let's thank the judges as well. Okay, now, so all of you can place your audience votes. Just put your name on the piece of paper, put it in the I guess your favorite speaker's container, and then go have a beer and some food outside after hour. Thank you.